Okay, so for example number 5, what we're going to do is we're going to select 3 cards. Out of a deck of 52 cards, right? Do you guys know that a deck of cards has 52 cards in it? And then it's what's the probability? So here's the question: what's the probability all 3 cards are hearts, and then they want us to do like a part A. So part A would be when you replace each card, you put it back in the deck, and then B would be without replacement. Okay, so right off the bat, when we replace the card, we know that that's an independent. Those are actually 3 independent events, and we'll talk about that in a second. And then dependent event. All right, so let's do part A. So when we do the probability, so let's choose some events, right? So the probability of A, where A is hearts, right? And B, where the second card is hearts, and C, where the third card is hearts, is actually equal to the probability of A. This is for the independent, right? Independent times the probability of B times the probability of C. Does that make sense? Now, if I replace the card back in, the probability of A is there are 52 cards total. What are the odds of me reaching in there and pulling out hearts? Well, there are 13 hearts in the deck, so I've got a 13 out of 52 chance of doing that. If I put the card back in, I still have 52 cards. What are the odds of me pulling out hearts again? Well, if I put the card back in, I still have 13 hearts in the deck. And then again, for part C, I have 52 cards in the deck. Okay? So then if I multiply all this out, this is equal to 1 over 64 because it'll reduce down to a really small number. And so the probability of this occurring is going to be 0.016, which is about, remember we moved the decimal 2 places, 1.6% chance. So a 3, if I pull 3 cards out of the deck and I put them back in the deck both times, or all 3 times, I've got a 1% chance, 1.6% chance that all 3 cards will be hearts. Okay? Now, that's because I'm replacing the card. Now, for part B, this is a little trickier because we're putting it back in. So, this is for a dependent. When I pull out that first card, now I have different cards. That changes the probabilities. And so the probability of A being hearts and the second card being hearts and the third card being hearts, now that formula is a little different. It's going to be the probability of A times the probability of B given A times the probability of C given that both A and B occur. Now let me explain that in regular language. So the probability of A pulling a heart out of the deck first draw. Then this probability is given that my first card is a heart, what's the probability of the second card being a heart? And then the last probability is the third card being drawn as a heart, given that the first and the second card are both hearts. Okay, so now this is easier than you think. When I pull that out, I've got a 13 out of 52. There are 52 cards in the deck, and there are 13 hearts. When I pull it out, this is also without replacement. Okay. So now, on the next scenario, what's the probability of me pulling out a heart? Well, it's really, there are only 51 cards left in the deck, and only 12 hearts, because I pulled one out and I didn't put it back in the deck. Then, in the next scenario, what are the odds of me pulling out a third heart? Well, now there are only 50 cards in the deck, and only 11 of them are hearts. So now when I multiply this out, I'm going to get 11 over 850. It reduces down, which is approximately 0.1 or 0.013. If I move the decimal over 2 places, it's approximately 1.3%. So now this will be a scenario where I'm trying to determine, let's say I make a bet with somebody and I say, well, deal me 3 cards and I'll bet you that all 3 cards are hearts. Well, that if I do that 100 times, only 1.3 times will it occur that it's actually all 3 cards are hearts. So it's a very low probability. So if you ever watch like on TV where they play Texas Hold'em and they calculate the probability of people getting certain hands and stuff, this is sort of how they do those calculations.